Hello and welcome! In my last video about the exciting hybrid 386-486 mainboard, I upgraded it to support 3V 486 CPUs. It was actually a very simple upgrade since a 486 doesn't pull a lot of current and I could use a regulator off the shelf. And today I would like to talk about a voltage regulator again, but this time a bit more sophisticated. I'm coming back to a topic which I started more than a year ago and unfortunately couldn't finish back then due to some tragic circumstances. I had to put most of my projects on ice, but now I'm glad to announce that I finally found some time to continue what I started. If you are a long-time follower of my channel, you probably already remember what I'm talking about. If not, I would strongly advise to watch the two videos which I made over a year ago. The links are in the description. For brief recapitulation, I got this Asus Pentium mainboard which didn't support dual voltage CPUs like Intel Pentium MMX or AMD K6. Pentium 166 was the fastest what was possible, but it had a feature connector for a voltage regulator module which would allow to use faster and more modern CPUs in it. Unfortunately, such VRMs are hard to find and are very expensive, so I decided to develop my own. After a lot of back and forward, I designed this, and it could eventually power the dual voltage CPUs, but I also had to do some modifications to the mainboard to convince faster CPUs to work properly in it. Once again, if you didn't see or don't remember how it started and which issues I had to solve, feel free to take a look. The last part ended with an experiment where I got an AMD K6-2 at 400 MHz in this board. Quite a huge difference compared to the officially supported 166 MHz. However, I initially had only Pentium MMX in mind, which pulls only up to 5.7 amps of current. And a K6-2 would push this VRM with its 11 amps hunger far beyond its limits, which are at around 6 amps. Well, my experiment was successful, but the voltage regulator module became very hot and it was clear that I need another solution. In the first revision, I used a very simple circuit with highly integrated DC-DC converters, which was easy but also insufficient for my further plans. So I decided to dive deeper into this topic and design an efficient synchronous VRM. First of all, I have to admit that this is my most challenging project so far. For an electronics engineer, this is probably an easy walk between breakfast and the first meeting of the day, but I'm a software engineer. Of course, I had some theoretical knowledge from the university, but I was really inexperienced in designing a power supply circuits from scratch. I can program whatever you want in various programming languages. Also, digital electronics is a topic where I feel confident, but power or analog circuits are definitely my weak point. At least I think I could improve that quite a bit. I started this project because I wanted to learn more about switching power regulators in depth, and boy, there were a lot of gaps to fill. I read a lot of literature and datasheets, learned a lot of things about ESR, why it is better to use many smaller capacitors than a larger one, for example, how different parts react to different frequencies, what's the difference between synchronous and asynchronous switching voltage regulators, how to calculate all the parts, and much more. Unfortunately, it would be an overkill to put all that details in a video, or even in 2, 3 or 4 parts, so I'll try to stay away from the complicated theory. However, I found that very exciting and revisited even some of my hard time defective parts using the new knowledge, and it helped me to localize the issues indeed. But that's for another day. So, shortly before I had to interrupt my work on this project a year ago, I already had this revision 0.2 prototype working. As you already see, this has nothing to do with the first revision. It was a completely new development. My aim was to get something what would be able to handle at least 11 amps. Maybe more to have some safety buffer. To reach that, I decided to design so-called synchronous switching voltage regulator. Without going into details, it's a regulator circuit which is built of a DC-DC controller, which switches two NMOSFET transistors alternatively. In an asynchronous regulator, one transistor is replaced by a diode, and DC-DC controller has to control only one transistor. Synchronous regulators are slightly more complicated, but also more efficient and more interesting, since modern mainboards, graphics cards and other hardware today usually use synchronous regulators. So, despite of the completely different approach, let's see what has been changed and what didn't change in revision 02. Obviously, in the second revision there are a lot more parts and almost all of them are SMD. So, on the bad side, it is now more effort to build it, but I used bigger 1206 SMD parts and solder pads optimized for hand soldering. With a little bit of practice, it is not too complicated, to be honest. Also, all the parts are now on the one side, and on the other you can find extended voltage table. The second revision got 4 switches instead of 3 as before, and the voltage range was increased. Now it goes from 3.2 volts, as officially required for K6 233 CPUs, for example, down to 1.6 volts. As I presented the first revision, there were some comments that it would be nice to have voltages for mobile AMD K6 2 and 3 CPUs. And here you go. On the other side, 3.2 volts can be used even for single voltage CPUs, which would be slightly undervolted, but usually run fine at 3.2 volts instead of 3.3 volts. This is quite a huge range of voltages, and this was one of the issues which I had to fight with. The output voltage of the regulator is controlled by a voltage divider on the output and feedback to the DC-DC controller. Calculating the resistor network for the voltage divider was not complicated. A table with some formulas and a list of available resistors in the online shop did the trick. However, a switching voltage regulator is quite a sensitive circuit, which runs the best at one defined voltage. You can calculate the best fitting parts, which would keep the efficiency high and the ripple as low as possible. But as soon as you want to increase the range of the output voltages, you have to make some compromises. You have to work with ranges, and the calculations are getting more complicated. It is not possible anymore to find the perfect fit, and you have to tweak the parts in the equations, so you get the best results in average. And this is what I did. A lot of calculations, equations, graphs and trial and fail approaches. Yes, trial and fail. This sounds strange, but the power supply circuits are such a delicate topic that even in the datasheets of the DC-DC controllers, manufacturers write that calculating the values is not enough, and you will end up trying to find the right values by trying different combinations by hand. And this is what I did. I tested, tried another values, corrected my calculations and tried again. This was incredibly time-consuming, but with my oscilloscope, different parts, pen and piece of paper, I eventually found the balance, but not with this revision. Well, it worked, but the design was not yet good enough. I got a lot of voltage ripple, about 200 millivolts, twice as much as normally allowed for Pentium MMX, for example. I tried to get the ripple down, but eventually I was limited by the design flaws. My main problem with this revision was the space. I tried to keep the module the same size as before, especially in the beginning. I didn't want to make it wider. On this board here there is a lot of space left and right from the module, but I didn't know how about a module somewhere else. I was limited in the selection of capacitors, in their amount and in wiring on the PCB. I used some wire networks to bring the copper planes from one side of the PCB to another, which shouldn't be done in a good design. Well, this is something I had to learn as well. Then months passed and I had no time to come back to this project, but one day I suddenly got some spare time and spontaneously decided to make at least a repairathon. Maybe you remember my series of videos last autumn. One of the boards in that repairathon was this Gigabyte Socket 7 mainboard. And the interesting thing about it is that it also has the same VRM connector. However, this board has it completely with full socket, including throw-out levers, on the sides. I compared dozens of other boards on the RetroWeb database and would consider this as standard, so there was no need to keep the module smaller than it could be. Again, months passed and a couple of weeks ago I finally could come back to this exciting project. I dug out this gigabyte mainboard, measured everything properly and designed the revision 0.3 with all the improvements I could identify so far. The difference between the second and the third revision is not that big anymore. Improved wiring, improved layouts, better and more filter capacitors. The switches are the same, the voltage range as well, from 3.2 volts down to 1.6 volts. Just ignore the hanging capacitors and gaps now, this is because I'm still experimenting and waiting for the delivery of proper parts. Now the module is wider and fits perfectly into the socket. The levers on the sides lift the module out of the socket as intended. By the way, there were some comments about the first revision that I had to put the parts on the other side of the PCB to let the CPU fan cool them. Well, first of all, as you see, if the parts would be on the other side, they would not fit between the VRM and the CPU cooler. Second, the orientation and location of such a VRM feature connector is always different on various mainboards, so doesn't matter which direction the parts would face, there will be always a board where they wouldn't look away from the CPU fan. However, the planes under the DC-DC controller and the transistor are interconnected with wire grids on both sides, so the heat should be transferred also to the other side of the VRM module to dissipate there. This is about the development of this project so far. I didn't record the development because most of the time it was me reading or calculating something, but I would like to show you how I developed and tested the VRM. Of course, I didn't want to kill the mainboards, so for testing and measurements I used a lab power supply where I can limit the voltage and the current and which delivers a perfectly smooth voltage. The power supply was set to 5 volts and the starting current was limited to 1 amp, so I wouldn't burn down my house in a case that there is a short. The clamps would go to +5 volts and ground to the VRM accordingly. It is a bad idea to run a switching voltage regulator without a load, so I used a power resistor between the ground and the output pin. I used 3 resistors, 10 ohm, 1 ohm and 0.3 ohm, which gave me the current of 300 milliamps, 3 amps and 10 amps. The resistors have to dissipate a lot of heat and shouldn't be used for a longer period without additional cooling. Here I use a 10 ohm resistor which gives the lowest current but also can be used much longer. To measure the ripple, I connected the oscilloscope directly to the resistor. The module is designed to behave the best between 5 amps and 13 amps. But it runs also with up to 15 amps or only 100 milliamps. But if the current is too low or too high, the ripple increases significantly. Still, it remains constantly below the allowed 100 millivolts, and with a decent load I'm getting values under 50 millivolts. But I'm currently waiting for some parts, and if my calculations are right, I'll be able to push the ripple even further below 50 millivolts. However, with even 60 or 70 millivolts ripple by 3.2 volts output, it is totally within the limits and would power any Intel Pentium CPUs reliably. Please don't forget that this is still a prototype. Here I have a second VRM where I have slightly different parts, as you see, so I'm still experimenting. Okay, let me show you the voltages. Now all the switches are off and we have 3.18 volts. This is near enough at 3.2 volts. Now we should get 2.9 volts. .88 volts is again near enough. .78 volts for 2.8 volt setting. This is an interesting voltage for the normal Pentium MMX, for example. I will not go through all the voltages now, but let's try another interesting voltage which we would need for the AMD K6 too. 2.22 volts for 2.2 volt setting is also fine. And last but not least, let's try the lowest possible setting. 1.64 volts should be also near enough at 1.6 volts. All voltages are within the specs, and as you maybe noticed, the ripple was, with all settings, nearly identical. At 3.2 volts it's good, and at 1.6 volts we should try to get it down, but I'm still working on that. Okay, let's give it a real task. First, I wanted to show you directly a Pentium MMX, which needs dual voltage with core voltage at 2.8 volts. But then I looked at this gigabyte mainboard with a Pentium 100 in it and decided to start with this 3.3 volt single voltage CPU. As I showed in my last video, usually the VRM feature connector could have some jumpers installed to bridge the I/O and core voltages and run everything at 3.3 volts. This job would be then done completely by this linear voltage regulator, which often gets very hot, especially with the faster CPUs like the non-MMX Pentium 200. Since the VRM module, which I designed, can deliver 3.2 volts as well, it can be used to power the single voltage CPU. It's not 3.3 volts, but still close enough. It should relieve the onboard linear voltage regulator, and we wouldn't need to replace the VRM module with jumpers every time when changing the CPUs. And as you see, the system started. The CPU is Pentium 100, but I didn't connect the keyboard nor any drive, so it will not boot now. The CPU is already warm, it's not critical, but let me put a cooler to avoid unneeded overheating. The linear voltage regulator is on the other hand stone cold, which means that it doesn't power the CPU currently, and the VRM module is also absolutely cold. Not even a little bit warm, but a Pentium 100 is not a challenge at all for this regulator, so no wonder that it remains cold. So far, single voltage CPUs should be fine with this VRM. Let's move on to the mainboard which brought me to the idea to make this regulator at all. The Asus Socket 7 mainboard, where I added the VRM feature connector in the last video. It has still the Pentium MMX 200 in it, which is waiting hungry for some electrons. So the VRM has to be set to 2.8 volts, the core voltage of the CPU. Unfortunately, on this board there is only the pin header and not the full connector, so the VRM can be accidentally inserted the wrong way around. So it is important to check that it has the right orientation and the pins are all aligned properly. Let's add a graphics card and the compact flash to IDE adapter with MS-DOS on a compact flash card. And as you see, the system is booting just fine. Let's make some stress. The voltage on the CPU is 2.796 volts. I consider this as perfect. The VRM is still absolutely cold. The system is running, but I didn't do long-term tests yet. As I said, I'm still experimenting, tweaking the settings. I'm currently waiting for some new parts which should arrive in the next days. This is a revision 0.3 and I'm almost happy with it so far. Still, during the tests I made some minor improvements and already planned the next revision, 0.4. It is almost the same as 0.3, but will hopefully bring slight improvement in regards of ripple. Otherwise, I updated the silk layer, labels and the documentation. The project is nearly ready to be released. So, if you are excited just as much as I am, please join me in the next part where the missing parts will be hopefully arrived, so we can make some longer tests and see if it will power an AMD K6-2 reliably. If everything works as planned, I'll open source this project just as I always do, with documentation, BOM and Gerber files, so you should be able to build such a VRM yourself. So far, I hope you enjoyed this video, thank you for watching and goodbye.